Hello students, welcome back to the online course on the topic arbitrary counter. Before starting about the arbitrary counter, I want to regain you about the concept on the counter. What is a counter? A counter is a circuit that is a combination of flip-flops in which they are connected in a certain way so that it can able to count the given sequence. Two type of counter are possible: synchronous counter and the asynchronous counter. What is a synchronous counter and a asynchronous counter? If all the flip-flop in the counter are having the same clock pulse means are sharing the same clock pulse means then it is called as a synchronous counter. If that is not the case, the output of the previous flip-flop is connected as a clock for the second flip-flop means then it is called as a asynchronous counter. What is the meaning of the asynchronous counter? Without the output generated from the previous flip-flop, the next flip-flop operation is not considered. That is called as a asynchronous counter. One more point is that if it is a synchronous counter, both the fixed sequence and the random sequence counting are possible. That means, what is a fixed sequence, what is a random sequence, that we have to understand now. What is a fixed sequence means up counter, down counter are the example for the fixed sequence. That means if I say it is a 3-bit up counter, then what we will say, starting from 0000 to 111 we will say that is a normal 3-bit up counter. That means after 000 is going to come, after 001 010 is going to come. Therefore you can able to predict the sequence, that is called as a normal fixed sequence. If it is a random sequence means the order of the sequence cannot be predicted. For example, take the question given on the left hand side of the page. Design a counter to count the sequence of 0 1 2 4 5 6 using D flip-flop. What is the sequence there? 0 1 2 4 5 6. Is it following any order there? It is not following any order. Therefore it is an example for the random sequence. The other name for the random sequence is a arbitrary sequence. Therefore now we are going to see about designing a random sequence counter, that is coming under the topic of synchronous counter, right? In the if it is a asynchronous counter or the asynchronous counter, then only fixed type of counting is possible. Clear? Right, before starting our given question, I want to regain you about one more point. What are the design procedure in the synchronous counter? First step, we are going to design a counter. That means it is going to have a group of flip-flop. What type of flip-flop? Second thing, how many flip-flop are needed? The total number of count of the flip-flop. Therefore, I can able to say how many counts are possible, how many different states are possible, right? Therefore, what type of flip-flop, then how many flip-flops are needed. Third thing, what is the sequence that is going to be generated at the output? Based on that one, we have to create a state table. From the state table, with the help of excitation table, we have to find the flip-flop inputs. Then the flip-flop inputs expressions are find out with the help of K-map. Then the K-map expressions are converted to the logical diagram in terms of flip-flop. Correct? This is a normal design procedure in the synchronous sequential circuits. Now we can start with our question. I want to tell one more example for the arbitrary counter. Before starting our question, I can able to say some more examples about the arbitrary counter. The examples of the arbitrary counter, I already said if it is an arbitrary counter means it is not going to follow some normal, it is not a normal up operation or the down operation. The counting sequence can be a random one. It cannot be predicted what the next count it is going to come. Therefore the left hand side random sequence is a 0 1 2 6 7 8 or it is not following any other node. Therefore this is an example for the random sequence, is an example for the arbitrary counter. We already know two counters that are ring counter and the Johnson counter. What is a ring counter? If there are n number of flip-flops are connected in a SIPO order means then only one flip-flop is going to be produce the output as a 1 and the remaining things is going to, there is going to be only one data is there and the one data is going to be circulated again and again in the circular way throughout the shift register mode. Correct? That is called as a ring counter. What is the order for that one? If I want to say that in terms of number means that is a order of 8 fold to 1. Therefore 8 fold to 1 is a sequence order, means then it is a ring counter. It is not a, it is a random sequence. Similarly Johnson counter, one by one the output has to be increased, then one by one the output has to be decreased, right? Then it is a Johnson counter. It is going to have some order, that is a 0 8 12 14 15 7 3 1. It is following some certain order. It is also a random sequence, right? These are some of the examples of the arbitrary counter. Ring counter and Johnson counter are also the example for the arbitrary counter. Then what are the what is a excitation table and what is a state table? What is excitation table? We already know the characteristics table for the flip flop. That means based on the flip flop input and the present state, I can able to predict what is the next state. That is a characteristics table. What is excitation table? I know the present state, I know what the next output is going to come. That means I know the present state as well as the next state. By comparing the present state and the next state, I have to say I have to predict what input that is changing the present state to the next state, right? That is if I'm going to create a table for that one for in terms of flip flop, means then it is called as a excitation table. In case of D flip flop, means I have to compare the present state of q and next state of qn plus 1, and I have to predict what is d value, so that qn is converted to qn plus 1, right? That is a excitation table. The next one is a state table. What is a state table? If I'm saying about only one flip flop, what is how the flip flop is going to work in terms of excitation table? If I'm saying the complete circuit in terms of present state, next state, and what can be the input that is going to make this change, means then it is called as a state table, correct? We have already discussed the design procedure. Now we can start with our question. What is our question? Design a counter to count the sequence of 0 1 2 4 5 6. Therefore what is the first thing? What is a flip flop? What type of flip flop we are going to use? The question is given as a D flip flop. Second thing, how many D flip flops are needed? How many D flip flops are needed? Already we know the formula. To calculate how many flip flops are needed, the formula is 2 power n should be greater than or equal to capital N, right? Where the capital N is the count and small n is the number of flip flop needed. By seeing this one, we can able to predict that the number of flip flop needed is 3, because total number of count is 6, correct? Then what is the sequence that is going to be counted now? 0 1 2 4 5 6. Again 0 1 2 4 5 6. This is going to be repeated again and again. Therefore the sequence is 0 1 2 4 5 6, correct? Now we can start with our state table. If we want to complete the state table, means we have to be very clear with the excitation table of the D flip flop also. Therefore what is the excitation table of the D flip flop? Qn plus 1 has to be compared, and I have to predict what can be the flip flop input that is making the Qn to be converted to Qn plus 1. In case of D flip flop, whatever the Qn plus 1 value is there, that will be the D value also, correct? Now we can go for the state table. What is a state table? It will have the present state, it will have the next state, that means it will have the present count, it will have the next count, and I have to say what input is going to make the present count to be converted to the next count. Therefore present state, next state, and the flip flop inputs. Since we are having a 3 number of flip flops, it is going to be QA, QB, QC, QA plus 1, QB plus 1, QC plus 1, and comparing QA and Q plus 1, there are 3 flip flops are there. Therefore the input for the 3 flip flop is DA, DB, and DC, correct? How many flip flops are there? 3 flip flop. Therefore how many cases are possible? 8 cases are possible. Therefore in the present state 8 cases are possible. The present state 8 cases are possible. Now we have to remember our sequence order. What is our sequence order? 0 1 2 4 5 6. Therefore I have to fill this term now. 0 1 2 4 5 6, correct? Again 0 1 2 4 5 6 is going to be repeated. We are going to consider only one sequence, right? take the first row. If the present state is 0 0 0 means what will after 0 what has to come? 1 has to come. Therefore 0 0 1 is filled there. Correct. Similarly 1 means 2 has to come. 3 means 4 has to come. Then see the fourth row 0 1 1. 0 1 1 is number 3. After 3 what has to come? We don't know. Correct. Leave the place. What is whatever we know first we have to fill that one. What are the empty places now that is not given in the question? If anything is not given in the question, then we can consider for the don't care operation. Correct. Therefore for the state 0 1 1 and 1 1 1 that is not given in the question, I am going to consider that one as a don't care. Correct. Now we are having the complete present state. We know the complete next state. By comparing the present state and next state, we have to write the flip-flop inputs. Right. For example, consider QA and QA plus 1 of the first row. That means for the flip-flop A, the present state and the next state is considered. See the excitation table. If 0 0 is there means then the D has to be, the flip-flop input has to be 0. Therefore I am marking the DA as a 0. Correct. Same way all the present state and next state variables are compared and the flip-flop input column is filled there. Flip-flop table is filled there for the 8 rows. Clear. Now what is the next thing we have to do? Whatever given in the flip-flop column DA, DB and DC, that has to be implemented in the K map and we have to find the expression. Right. For DA, DB, DC we have to find the expression so that it can be implemented in the logic diagram. Right. The present state is a QA, QB, QC. Three variables are there. Therefore we are going for the 2x4 K map. Take the DA column, fill in the K map and we can able to get the expression as a QA XOR with QB. Take the DB column, fill in the fill the contents in the K map and we can able to mark the K map as a DB is equal to QC. Similarly do it for the third column DC and we can able to predict the DC as a QB bar multiplied by QC bar. Correct. Now last step is a logic diagram. How many flip-flops are needed? 3 flip-flops are needed. What type of flip-flop? D flip-flop. Therefore D Q QC bar, D QB QB bar, DA QA QA bar. All the things are there. Why I'm writing from why I'm writing in this way? Because I'm going to form the diagram in such a way that it will look like from the diagram is moving from LSB to the MSB side. Right. Right. What is our first point? It is an arbitrary counter. Arbitrary counter means it is coming under the synchronous sequential design. Therefore all the flip-flop will have the same clock. Therefore all the flip-flops are having the same clock here. In case I want to reset the counter means I have to go for the reset signal or the clear signal. Then all the things are shared, all the flip-flops are connected to the common reset signal. If clear bar CLR bar is equal to 0 means then the counter will be going to the reset state. Third thing, I'm taking all the output of the flip-flop because QA, QB, QC, whatever the order we are seeing now, this is the same order we are going to see our output as a 0 0 0 or 0 0 1 or next state is 0 1 0. In this way we are going to see the output. Therefore QA, QB, QC is taken as the counter output. What is the next one? I have to connect my flip-flop inputs now, that is derived from the K map. What is we derived from the K map? The DA is equal to QB XOR with QA, that is connected in the for the input of the DA. Similarly what is DB? QC is connected there. For by the K map what we found out for DC is equal to QB bar multiplied by QC bar. Correct. Whatever the thing we have completed from the K map, that is implemented in the logical diagram. Clear. This is example for the arbitrary counter. Remember the design procedures are same as like that of synchronous counter. Only thing is the counting sequence is varying now. If there are any empty sequence means then that has to be filled with the, if there is any empty states in the present state or next statement, that has to be filled with the don't care operation. Clear. Thank you.